It's recording.
Thank you.
Okay, great. And it looks like numbers have stabilized a little, so let's start. Thanks everyone for joining for remote colloquium this week. And it's my pleasure to introduce our speaker for this week, Dr. George Clark. He has his bachelor's in physics from UNH and a PhD in physics from UT San Antonio in 2014. Following that, he did a postdoc at NASA's Goddard Space Flight Center. And then in 2015, he moved to Johns Hopkins Applied Physics Lab, where he's been ever since. And his research is focused on kind of plasma and auroral processes in magnetospheres of outer planets. And he's been involved in a number of different missions and instrument teams. He's project scientist for the JEDI instrument on the Juno mission. He's science lead for the JOE instrument on ESA's upcoming JUICE mission to Jupiter, and deputy lead for the IMAP Ultra instrument. And so I think today he'll be talking to us a little bit about Jupiter. And so I'll turn it over to you, George. And just a comment for everyone, make sure your mics are closed unless you're speaking. And at the end, we'll have time for questions where you can either type your questions into chat or raise your Zoom hand. And then last quick announcement is just that following this colloquium, we'll leave the Zoom link open. And for folks who want to have more discussion, we can kind of have group discussion after 1:40 p.m. Mountain Time. So go ahead, George.
All right, thank you very much, Lauren. And thank you for the invite to you and the committee members. And I wish I could be there in person. However, you know, just like everyone I'm sure is feeling like the Delta variant, and the fact that I have a son that's not vaccinated yet just kind of, you know, changes the calculus a little bit. So thanks for being accommodating, and hopefully I can make it out there in the near future. So yeah, I thought maybe just a quick picture of the, you know, the so-called human side of me. Lauren, you can see the slides and everything's fine. Okay, great. So yeah, I grew up in New Hampshire in a very rural part near the White Mountains, just south of the White Mountains, if you're familiar with that, you know, great hiking, skiing. And then like Lauren said, I moved to Texas for grad school. And now I live in Maryland. And I think all of New Hampshire has like 1 million people. And then in this little corridor that I live between Baltimore and DC, I think it's like, you know, several million. So that's, it's quite the experience. But yeah, you know, we love to kind of do outdoor things as a family. And here's a picture of my son trying to make pasta. He was recently diagnosed with celiac. So we're trying to make all the, all the sweet desserts and everything like that, and also his favorites like pasta, but now the gluten-free variety. So that's kind of been a fun challenge for us. But yeah, I think moving on. So here to talk about Jupiter's auroras, and especially now is kind of a great timing because the Juno mission, which I'll talk more about in a little bit, just finished its prime mission. And so this talk is meant to serve as kind of an overview of some of the highlights that Juno has kind of revealed over the various auroral regions at Jupiter, and kind of piece together some mysteries, some things that were different from Earth, and maybe even like, where do we go from here? And so first of all, I'd like to just say a quick thank you to many co-authors for their contributions to this talk, ideas, and also graphs and things of that nature. So yeah, I'm afraid the talk will probably extend. It's probably longer than the time allotted, depending on how long how fast I speak. But I think I, encourage questions, and also if we don't get through all the material, that's fine. I think we can save some. Whoever is able to stay on the end, we can kind of wrap up a couple of ideas if people wished. So I thought I'd start off with maybe a couple fun things, not related to my science, but related to Jupiter. So maybe some of you have already seen this, hopefully. The Astronomy Picture of a Day featured a video captured by amateur astronomers that saw this bright flash of light kind of in the cloud tops of Jupiter. Replay that again. Right there, if you can see it. So the cool thing about this is that, not that these things are somehow rare, but the fact that we're seeing these, and I think they said from the brightness is something like the size of a bus. So just a cool thing that happened just recently. The next is Jovian McJupiter face, which I love just from the title, and you guys probably remember Bodie McBoatface from that online poll to name a submarine. I think it was a submarine. But anyways, this here is just a picture from Juno cam, which is on board the Juno mission, and it just happened to capture the clouds. As such, there's an arrangement of storms that make it look like there's kind of a face here. And then, Jovian McJupiter face was the name that stuck. And this was also featured on Astronomy Picture of the Day. So we will talk a brief, spend some time talking about magnetospheres and Jupiter's space environment, very briefly highlight NASA's Juno mission, and then move into the fun part, which is talking about the highlights from Juno's prime mission, specifically targeted to the aurora of the satellites, the diffuse and main auroral regions, and the polar regions. And I'll kind of give a summary of the new auroral highlights. And then if there's time, I'd like to maybe talk about what's next and plans to explore the space environments of other planets. So first off, the brief introduction to magnetospheres. So just in case, maybe this is outside of your field of expertise, I know this is a very broad group, but magnetospheres are simply just the regions of space where kind of physical phenomena are dominated by the magnetic field. Now, the magnetic fields don't have to be produced by the planet itself. You have, in our solar system, you have objects that also have induced field signatures because maybe they have atmospheres, ionospheres, and those electric currents in the ionospheres can kind of hold off the impinging solar wind and the magnetic field that is brought with it. And so that's what this kind of graphic shows, the different magnetospheric types and how they are configured depending on the body itself. So like Venus, for example, has this induced field configuration. And then Mars also has an induced field, but also has some remnant crustal fields, which adds to the picture as well. And then, of course, many planets in our solar system have their own dynamos. So these are dipole, or I should say, magnetic fields produced by in the core of the planet as a result of kind of the currents in the dynamo. So from these various ways to generate the magnetic fields, you kind of get these different configurations. And then, of course, the magnetosphere is also a source of, inside a magnetosphere, a very healthy plasma and energetic charged particle environment. And the way that is sourced can be different depending on the planetary system or planetary body. So plasma can be sourced from the solar wind, and the solar wind is kind of this wind of charged particles that emanates from the sun and flows outward radially and into the heliosphere. And so that brings with it primarily hydrogen, helium. And so helium is usually has a charge state of 2, and then high charge state of oxygen, which is usually denoted O6+. The planet can also supply its magnetosphere from its ionosphere with, for the example, for the Earth, it supplies oxygen, hydrogen, nitrogen, and helium. Now you might notice that for this case here, the charge states tend to be a little bit lower, singly charged ions, whereas opposed to solar wind might be higher charge state ions. And then, of course, moons can also play a role in supplying the magnetosphere with plasma. For the famous example, and we'll talk a lot about it today, is Io, which supplies Jupiter's magnetosphere with heavy ions, and primarily sulfur and oxygen. And the reason why we denote sulfur and oxygen with N is because the environment there is such that it produces multiple charge states of those ions. So once the plasma is, kind of fills the magnetosphere, there's kind of 3 characteristic motions associated with it. I'll play this video here that just illustrates. I think the three motions here, the gyro, bounce, and gradient curvature drift motions in the magnetosphere. And so this animation just shows how a particle can gyrate and bounce. You can see this motion right here, and also drift. And associated with that are three adiabatic invariants that kind of, with a prescribed electric and magnetic field, you can work out the constants of motion that are associated with each motion I just talked about. And those are invariants only under the conditions with how fast things in the magnetosphere kind of act. Like the gyro motion, for example, has a very fast, 10 to the minus 3 seconds gyro period. And so to violate that, you kind of need waves that oscillate very quickly. So the other thing I want to highlight from here is that associated with the motions of the particles, there's also this quantity called pitch angle, which is simply the angle between the velocity vector of the particle and the local magnetic field. This is important because as particles drift with a particular, or bounce rather with a particular pitch angle, they reach different parts of the field line, which are kind of illustrated with these blue lines here. Some particles have pitch angles that are very parallel to the magnetic field. And if that happens, the particles can actually make it far enough down the field line and interact with the gases from the planet, whether it be the exosphere or the upper atmosphere, and then through collisions, it can be lost to that system. And when that happens, you can produce auroral emissions, and auroral emissions is kind of an imprint of a loss process. And so on the left here is Earth, that shows the kind of these dipole magnetic field lines with electrons precipitating down. So they have pitch angles that essentially carry them far enough down to interact with the atmosphere. And those interactions can excite the gas, and then it produces photons of specific wavelengths. There's different types of auroral emissions. You can have discrete auroral emissions, and then you can have kind of, which, by the way, discrete are structured emissions, or you can have diffuse emissions too, which are kind of lack that spatial structure, but can be present nearly all the time. Earth is not the only planet that has aurora. There's also Mars, and we kind of talked about Mars, how that has this induced magnetic field geometry with the crustal fields. And even though that the field geometry looks very different, electrons can still precipitate on field lines and have access to the atmosphere to create those photons. Here is a snapshot of magnetospheres throughout the system, throughout the solar system. So Earth is something that we know very well, has been studied for many, many decades. And maybe we know less about the other planets, but we still have a snapshot of kind of the characteristics from some of the flyby missions and some of the orbiters that have been sent to like Jupiter and Saturn, for example. And so there's a whole gamut of different types of characteristics within a magnetosphere of any particular planetary body. Here we'll be talking about Jupiter, so I kind of highlighted this. And so you can see that the plasma densities can vary by orders of magnitude depending on what system of interest you have. But Mercury and Neptune, very low plasma densities. Earth and Jupiter, very high, something like greater than 3,000 centimeters squared. And then the composition can vary drastically too, whether it be from solar wind input or from its own moon or ionosphere. You can have ranges from Mercury, which is primarily solar wind and hydrogen dominated, something like Earth, which is ionospheric and solar wind, so you get H plus and O plus, and it also higher charge states O. Jupiter, hydrogen, oxygen, sulfur, and then kind of Saturn, hydrogen, water group products, and moving out to Neptune, you get hydrogen and nitrogen. And the sources of these, in addition to the ones I talked about, can also be from rings, and even Triton may provide the nitrogen, or likely provides the nitrogen Neptune system, and that can be kind of seasonally dependent as well. Now, the last thing I'll say about this is that the the dynamics of a magnetosphere can be driven by different things. Of course, Earth is primarily solar wind with some rotational driven dynamics. And then you kind of move towards the more extreme rotationally driven magnetospheres of Jupiter and Saturn. I'll kind of move on from here. So a general motivation for studying magnetospheres and auroral phenomenon is particle acceleration. And there's more than one motivation to discuss, but I'm gonna kind of frame it in particle acceleration, and hopefully that becomes clear why later in the talk. But particle acceleration is this phenomenon that occurs throughout many different systems and disciplines, you know, from astrophysical jets to solar storms to planetary radiation belts. And to understand the diversity of processes throughout our universe and what accelerates particles, you know, you got to study all the different systems and understand how they operate within that parameter regime. So an auroral phenomenon also is kind of the manifestation of several types of phenomena, including acceleration and loss processes. And the nice thing about auroral physics and auroral phenomenon is that unlike a magnetosphere where acceleration occurs over a very vast space, the field configurations of planetary magnetic fields kind of converge in the polar region. And so you can study acceleration and loss processes that occur in a very spatially confined area. It doesn't mean it makes our life that much easier, but there is something to say about having a targeted location to study these processes. This, by the way, was the Aurora from the Moon Magnetosphere Conference in Iceland a few years ago. And what was great about this was that it happened late at night, and it was really the best chance that we had during the whole meeting. And so people are running around in the hotel, getting everyone outside to look at the Aurora. And so we were in Selfoss, Iceland, and I think it was like maybe below freezing temperatures at this hour. It was like roughly midnight, and people were in their PJs, just absolutely freezing. But we were rewarded with this really, really awesome display. So like I said before, the Aurora aren't unique to Earth or even the planets. You know, we know that they happen at Earth, Jupiter, which I'll talk a lot about, even moons. Ganymede is this unique moon in Jupiter's system that has its own magnetic field, and it interacts with Jupiter's magnetic field. And there's a lot of precipitation of fairly energetic particles that produce the Aurora. And then, of course, we've seen radio emissions from distant worlds, such as this brown dwarf, and those are being interpreted as auroral emissions. However, we know nothing about their rotation rates or magnetic field strengths, or as far as I understand, and what could be sourcing the emissions. And so it's kind of logical to ask, what kind of information can we learn by studying the emissions of auroral phenomenon and being able to link that back into in situ physics. So Jupiter is a great case study in our solar system because we have lots of remote observations covering a wide range of wavelengths, from UV to visible and to X-ray. Jupiter, is also this kind of planet that is this fast rotation rate, strong magnetic field, and it might even be one of our best analogs for understanding worlds outside of our solar system. And so what we want to do with Jupiter and how we kind of frame this talk is understanding what we can apply for, what physics can we apply from Earth to Jupiter, and understanding how particles precipitate and are accelerated that produce these kind of complex emissions. And so understanding the diversity of the auroral acceleration systems and the limitations of how our knowledge can be transferred from Earth, I think is very useful in understanding how we ultimately understand how we scale these processes and the universality of them. So like I just said, what can we apply physical insight gleaned from comprehensive measurements at Earth to the other systems? And this is kind of a large motivation of this talk, and focusing on new discoveries from new discoveries of Jupiter's aurora from the Juno mission. So we will now move into Jupiter's space environment. So Jupiter is this has this magnetosphere that may look very similar to Earth in some characteristics. You know, you have a bow shock and a magnetosheath and a magnetopause. And then you also have like lobes and regions of closed, an inner magnetospheric region with a current sheet. But when it comes to scale, the Jupiter's magnetosphere is just very immense. Here's something. Here's kind of a picture denoting how Earth's and its kind of magnetosphere roughly fills the volume of space of just Jupiter itself. And I think if you could kind of see Jupiter's magnetosphere, in the night sky, I think it subtends like an angle maybe almost twice as large as the sun. So it's this really immense structure. And some other fun facts about Jupiter is it's this rapidly rotating magnetospheres with moons embedded in the inner region. And so this is an animation of Jupiter with these magnetic field lines painted as this orange color. And you can see the orbits of moons deep inside this magnetosphere. And so, for example, you see Almathea and Thebe. But then as you move out, you see that there's Io kind of in the background too, also orbiting Jupiter. But there's also this kind of, in this animation is depicted by this yellow color. This is the plasma torus that is created from Io sourcing plasma and neutrals into the Jupiter's magnetosphere deep within. And then the animation kind of zooms out a little bit more. You see Ganymede, and hopefully you'll see Europa eventually. But nonetheless, Jupiter's magnetosphere is unlike Earth in the way that there's many moons deep inside that kind of play important roles in the dynamics of its magnetosphere, unlike the moon here at Earth, which only kind of spends a small fraction of time in our magnetosphere and is not a major source of plasma. So this is to kind of highlight that again, but maybe talk a little bit more about Io. So Io is this geologically active moon, largely due to the tidal forces acting on the moon itself as it orbits Jupiter. And so the Io is able to spew material out through volcanoes, and it kind of resurfaces or provides a lot of material on the surface of Io. That material is likely like silicate and SO2, and then there's this atmosphere that is produced as well, and you can kind of get like local density enhancements from volcanic activity maybe, but that atmosphere is what and how it interacts with the magnetosphere of Jupiter is what provides a lot of the plasma in the system, likely through kind of electron impact, maybe charge exchange, and things like that. So the impinging plasma from Jupiter on the atmosphere of Io liberates material. This picture here again just shows the neutral cloud and the plasma torus and the Galilean moons kind of embedded in that region, and also the flux tubes that are associated with the moons too, and how they are filled with plasma and ultimately connect to the ionosphere of Jupiter. There's a large-scale current system that is generated from the rapidly rotating magnetosphere acting on material that is produced by Io. So there is a material from Io will want to co-rotate with the magnetic fields and kind of spin as with the rigid co-rotation. And that kind of like, I think the angular velocity goes something like 1 over v or 1 over r as you kind of go out. But what happens is the magnetic field lines begin to feel some stresses from the ionosphere when the material in the field line can no longer be kept up at rigid co-rotation from the field line that's rooted in the atmosphere of the planet. And so there's a torque setup there's a torque setup trying to maintain that kind of rigid co-rotation, and there are field line currents as a result. And these field line currents flow out radially and also field line that then close in the ionosphere. And there's acceleration regions that are thought to be associated with this system that further accelerates the particles to help close that current system. And this is what's highlighted as the impedance region. And so this is kind of like the Birkeland current system of Jupiter. And I'm sure many of you are familiar with the Birkeland current system at Earth. But that's not the only interaction between the magnetosphere and the ionosphere. There's also the satellite footprint aurora too, which is a slightly different interaction. There's a subalphanic interaction, meaning that the kind of the alphane and the fast mode Mach numbers are quite small, and so but that's the relative motion of the plasma and the satellites itself. And so when that happens, you don't form bow shocks around the moons, but rather you form these alphane wings. And these alphane wings carry with them current that then close in the ionosphere. And it's these interactions here that produce the famous footprints in the auroral regions that's seen, that were observed by Hubble. And so this picture down here below shows Io with its extended tail, Ganymede footprint, and the Europa footprint here. The auroral emissions from Jupiter, as a result of that kind of current system I just very briefly talked about, show kind of different characteristics. You have a somewhat steady main oval here with a kink-like feature here due to a magnetic anomaly. So there's a weak radial component in the magnetic field in this region of Jupiter's magnetosphere, or polar region rather. The Aurora co-rotates with the planet in what's called the system 3 coordinate system. And so unlike the polar region here, the main oval seems to be kind of almost quasi-steady, but you can see in the polar region it's very patchy with bright emissions occurring all over the place. And then of course you see this right here, I believe is Io, the footprint associated with Io. I'll play it one more time. The timescales with the polar emissions occur on the order of, minutes, tens of minutes, and hours, whereas these main emission is steady for much longer time periods. Although it's not to say that it's always steady, though. The main emissions definitely have changes due to maybe the solar wind and also dynamics within the magnetosphere itself, such as particle injections. So out of these pictures, people have kind of cataloged the auroral region of Jupiter, and this is the northern hemisphere. And you can see that there's really a multiplicity of processes that are present. The yellow highlighted ones are just some regions that I'll kind of discuss in the talk. But there are many more regions here with very, very interesting physics, but just time does not allow me to kind of go into that. So we'll talk mostly about the main emission oval. So this is highlighted by this number 1, so this kind of orange curve here. We'll talk about the footprint of the satellites, and I'll specifically focus on Io, so number 6. And then of course, some of the polar stuff here, which is highlighted for numbers 9 through 12. And so that's kind of generally this region in here. So now we're kind of getting into NASA's Juno mission. So hopefully I kind of set the stage of why it's exciting to explore magnetospheres and auroral phenomenon. A little bit of highlights from the Jupiter space environment, and then Juno was a spacecraft to go to Jupiter. It's a polar orbiting spacecraft to kind of study the interiors, the origin, the atmosphere, and the magnetosphere of Jupiter, with emphasis on the auroral physics, so the polar magnetosphere. So the Juno is a solar array, so solar powered spacecraft with these large solar arrays, and its diameter is quite large. It's about 20 meters in diameter, and it spins roughly once every 30 seconds. And on board Juno is a whole host of instrumentation to kind of dissect Jupiter's magnetosphere and interior and atmosphere. But it's really nice actually, because this is one of the few planetary missions that has a really healthy magnetospheric suite of instruments. So we have high energy particles, low energy particles, a magnetometer, and we also have a radio and plasma waves instrument as well. And then of course we have ultraviolet spectrometers for context and imaging, doing the global images of the aurora. So Juno's orbit takes it very, very close to the planet in a polar-like configuration. So Juno has these polar orbits that look like this on the bottom left. So you can see they come very close, something like 4,000 kilometers above the cloud tops, and then they go far out, roughly 100 RJ away from Jupiter. So the periods of these orbits are just shy of 2 months, about 53 days. And you can see how the orbit changes as a function of time. And that's because its periapsis hinges below the planet. And so what's going on is that we actually reach lower and lower altitudes over the Auroral region as time progresses. This is a graphic showing the kind of orbital evolution of Juno in Jupiter's ecliptic plane. And so we started over here with the orbit insertion, and then our first perijove. And so we call orbits perijoves, and so that's just how we categorize these. And so when I say PJ1, that's just referring to a particular orbit. And so now we're over here. We just finished, actually we just did PJ36, but the prime mission of Jupiter ends here on PJ35, which was just back in July. So just a couple of months ago. And like I said before, the apogee is beyond 100 RJ, and the perijove is very close at a fraction of RJ above the cloud tops. The Juno's orbit is unique also in the way that it kind of has this, very specific orbit to dissect all the different longitudes as it goes over the poles. And so it starts off with the first 4 perijoves mapped out this kind of 90-degree grid. And then as time goes on, every perijove had a longitude that would mean that the grid gets finer and finer. And so we are now, I think, sub 11.25 degree grid right now with all the orbits we've done. This is fantastic, by the way, for auroral science, because we cut through the aurora at very different regions all the time. And so this has really helped us understand kind of the all the auroral processes associated with like maybe local time and system 3 effects. Okay, I spent a lot of time on introduction and the Juno mission, and so this is kind of where the fun part starts. And that is to say that, you know, we can finally talk about some of the new results coming from the Juno mission. Really just a sample of some of the new results, because there's way too many to discuss in an hour. So we'll start off here with the main auroral region, which includes the, oh, no, sorry. Sorry, I lied. I'm going to start off with satellite footprint aurora. But first I wanted to just show a little bit here, the kind of differences. So on the leftmost image is a graphic from Earth that shows the auroral oval. And this is from NASA image. And what you can see here, and it's not always true, but I think it's mostly true, that there's kind of the polar region inside is kind of void of emissions. But you get this oval here that's usually associated with the open-closed field line boundary. I think, pretty sure that's true. But with Jupiter, you see that the right away that the emissions are very different. Not only some of the ones I talked about earlier with like this kink-like feature and the satellite footprint aurora, but also the polar region is full of emissions, as opposed to kind of the lack of emissions that you see with Earth's case. And so that is a high interest and something that we are really actively pursuing and trying to understand. But first, we'll start off with the satellite footprint aurora. Here are 2 images right here on the left and the right that are taken from the infrared camera on board Juno. The infrared camera named Jerome was able to resolve some spatial structures of Jupiter's or Io's auroral tail, which are really fascinating. First, this bifurcated tail here, which I believe the idea is that it's associated with Alphanic process, but I think there's still a lot of work to be done on exactly why it bifurcates. But nonetheless, you get this splitting of emissions associated with the tail. And then over here on the right, you can kind of see these blobs right here that occur down tail of the main spot. So that's the kind of field line that threads, the Io's main Alphane wing. And so, but down tail, you see a lot of these dynamic features, and that's likely thought to be due to the turbulent nature of Io's tail in the magnetosphere, and that's its imprint on in the aurora that it makes. We'll start off with plasma electrons. So these are in the Juno world, these are less than 100 keV electrons, and so Jamie Sully recently wrote a really nice paper kind of summarizing the emission or the observations of electrons associated with Io's footprint tail. And on the far left graphic, I'll kind of walk through this first, where you see a picture of Jupiter here, and there's this cylindrical projection, and you see a field line that maps to Io. The Juno spacecraft crossed a field line at roughly 1.6 RJ that mapped to the footprint tail. And when that crossing occurred, what the plasma electrons see are these enhancements in electrons with these kind of broadband kind of energy-like distributions with a cutoff maybe near 10 keV or so. And the other interesting thing is that you can see that there's a clear bifurcation between A and B. So this here is thought to match that kind of bifurcation I just showed in the infrared emissions. Associated with that are the angular distributions of particles. So these are the pitch angles, which I talked about earlier. These pitch angles show bidirectional distribution. So, precipitating electrons into the atmosphere, really creating the emissions that the ultraviolet camera sees with empty upward loss cones. So this is the flux that does not return because it's been lost. So if you look at the characteristics of these electrons on the field lines that thread Io in the auroral tail as a function of this what Jamie calls Alphane distance, and we can talk about later what that is, but essentially it's an angle that they define between the main Alphane wing and some Alphane wave trajectory that where Juno crossed that maps to the equatorial region. You see that there's an exponential trend with the energy function, with the energy fluxes as a function of this angle. So these are kind of well behaved, and maybe thought that maybe the reflected Alphane waves produce more emission or something like that. There's this one case here, 12N, that I wanted to highlight, where it is believed that Juno crossed actually through the main Alphane wing of Io, and then that's why you see this outlier and this really, really strong precipitation of electrons that produce very bright auroral emissions. So I want to kind of take a detour and talk about 12N specifically, because there's a lot of information that we're able to get from this. So here is a contextual image of Juno when it crossed the Io's footprint tail. So this red trace is Juno's footprint magnetically mapped to the 400 kilometers above the auroral region. And you can kind of see here where the spacecraft cross the tail-like structure. And during that crossing, what we saw was a host of plasma waves associated with the footprint tail or the main Alphane wing. We saw these. So this is the frequency of the plasma waves plotted as a function of time. And so this right here, this short 30-second time frame is associated with Io's footprint. And what you see are the dispersionless wave signatures, likely due to maybe part of the Alphanic branch. And then you can see waves that propagate up to the proton cyclotron frequency. And so these are likely ion cyclotron waves, and then you can see emissions that continue up to the electron plasma frequency. And so the power in these waves were extremely high. I think Ali calculated something like 600 EV per second heating rate associated with the ions. And so that there is fairly significant because that heats the ionospheric plasma. And we'll show you an observation of that in just a minute. Next, I want to show the low frequency alphanic fluctuations associated with the footprint tail. So as Juno crossed the tail in the same perigee of 12, you can see here, it might be hard to see, but right here, so roughly 920, there was a very sharp increase in the alphanic power, or in the power in the alphanic fluctuations associated with IO. And so Dan Gershman noticed this in 2009, and he also noticed that there's some weak alphanic or power associated with the other moons as well. And when you look at this and kind of plot it as a function of longitudinal distance from the IO footprint tail, you see that this PJ12 case, which is fairly low altitude and in the high B field region, produces a few thousand milliwatts per meter squared of Poynting flux. And then he shows also the other perigeos plotted to show two things. One, PJ12 is kind of in its own class, being factors of 10 or more greater than these other crossings here. And only, maybe only a factor of 2 or 3 than the PJ5 North case, which, by the way, we believe did not cross the main Alphane wind, but very close to it. So this is to say that there's a lot of wave power that that is being generated by IO because of its local interaction, that is then available to the particles to accelerate them and to produce the emissions that we see with the footprints. The other thing that we discovered was the presence of very energetic ions streaming away from the planet associated with the tail. And so here's a plot of the proton energy as a function of time and the angular distributions of the protons. And so here's the tail region, and also kind of the power associated with the alphanic low frequency B field, and then also the plasma waves here. And you see everything kind of coincides nicely in time. And so the distribution of the protons, the angular distribution, told us that this is likely what we call conic, but really it's just a very energetic part of outflow. So cold ionospheric ions are being heated to immense energies, are being lifted up out of the ionosphere and populated in the field line. This was of high interest because it wasn't really predicted that this would be a feature of the satellite magnetosphere interaction, but we see that it's actually a very very energetic feature associated with Io and Jupiter. We were able to put everything together, and I'm just looking at the time, sorry. We were able to put everything together for a very nice multi-instrument analysis to kind of understand some of the physics that are going on with Io's interaction with Jupiter as a proxy for satellite magnetospheric interactions. So the basic idea is that with this PJ12 account, the cold ionospheric ions in Jupiter's ionosphere basically are seed population that then gets trapped in this wave turbulent region, which we observed with Ali and Dan's work, both ion cyclotron waves and also alphane waves. And so the ions here are likely heated via cyclotron resonant frequency with the ion cyclotron waves. And so as they're continually heated, they eventually overcome this mirror force, which goes like the gradient of the magnetic field, and then they kind of get lifted out and drift along the field line. So further away where Juno was situated, we saw the result of that process because of the ion distributions that we observed. And the fact that you have these bidirectional electrons at the same location that we observed is likely kind of the smoking gun for the free energy source of the waves. And so all together, we believe that the alphanic perturbations generated near Io generates the anisotropic, sorry guys, talking too much here. So the anisotropy in the electron distributions that then drives provides a free energy source of the waves that then interact with the ionospheric ions. This multi-step process is actually of high interest because we know it happens at Earth, but this is kind of a different configuration or a different parameter regime that we can probe these details. So the energetic part of this outflow, or connex as we call it, happens in other places in Jupiter's Aurora too, but so far to date, the outflow associated with Io's footprint tail is by far the most energetic. And so the plot on the right just simply shows intensity as a function of energy. So these are energy spectra, and these are associated with the main Alphane wing, Io's main Alphane wing, the main auroral region, and the polar auroral region. And you can kind of see how the hierarchy here of the energy content as the different auroral regions. Okay, so now we are moving on to the main auroral region, and I have just over 10 minutes, so we might have to cruise through this. So first off, the discovery of the Birkeland current system with the high latitude measurements of the Juno magnetometer. So here, as Juno crossed over the polar region, it saw the fluctuations in the magnetic field that are imprints of a field line current system. And so this azimuthal perturbation in the field was strong, but something like a few hundred nanotesla strong. What's really interesting about this is that the expectations of the perturbations in the field were originally thought to be much larger. I think on the order of almost as high as 1,000 nanotesla. And so there's some right now, in particular, the Lester group, Anisha Carmen, and work with Emma Bunce, they're kind of comparing it with their model. And indeed, they're seeing that a lot of the crossings are much weaker. And so that's kind of a big mystery right now is why are the perturbations weaker in the Jovian system? Next, Juno identified kind of 3 distinct auroral regions in the main aurora. So one being the diffuse aurora, so where trapped electrons in the magnetosphere scatter into the atmosphere via pitch angle scattering. The other zones are, and this is kind of highlighted, maybe in this energy spectrogram plot, but I won't go into detail in the interest of time. The other zones are characterized by downward electron inverted V's. So these are parallel potential driven distributions by the fact that there's these quasi-static electric potentials located somewhere on the magnetic field line that are generated and accelerate particles to immense energies into the atmosphere. And then in the zone 2, they find that there's a lot of bidirectional acceleration. And the bidirectional acceleration right now, but it's also kind of being challenged, is thought to be associated with stochastic processes and specifically kind of Alphanic perturbations that provide little kicks in both directions of the electrons. The downgoing electron spectra appear to be broadband in nature and extend up to several MeV. And so on the top here, you have intensity as a function of energy, and you see that these broadband electron distributions are often formed. And so these are kind of characterized like, I think 90% of the observations are broadband electron distributions, and they carry with them some of the most energy flux to produce the brightest aurora. Some work being done to see exactly how the aurora is structured, whether it's through the turbulent interactions that produce those broadband aurora, or if it's more like the night relationship that doesn't produce, but that can characterize the strength of the quasi-potential magnetic parallel field to accelerate the particles in the atmosphere. So here, just the plot of energy flux in the energetic particles as a function of the characteristic energy, we're able to show different theoretical mechanisms and see what they expect. Unfortunately, things look pretty consistent to the different theories. So there was no smoking gun here, but like what's interesting is that we were able to kind of look at the different inertial scale lengths and how that produced and kind of the energy fluxes that those were produced. But in addition, What is being done now that's kind of new work is that Ali Suleiman at Iowa is putting together all the particle data and of course the magnetic field turbulence to see exactly if those broadband distributions are supported by the idea of Alphanic fluctuations. So let's disregard the top two panels, and in the third panel down is a plot of the transverse B, which I showed earlier. So the power in the Alphanic fluctuations, and overlaid is this perturbation here in the magnetic field, the characteristic of field line potentials. So, or field line current, sorry. Below is the particle signatures of a zone 1 region. So these here are kind of bi-directional electron distributions that create very bright aurora. What Ali is finding is that the turbulence associated with the Alphane waves doesn't seem to correlate with the region of where a lot of broadband distributions are occurring. So that's very interesting, actually, and we're unsure exactly what that means. So I believe it's a big mystery right now is how are the acceleration mechanisms set up, and what is power in the bright aurora at Jupiter. So next, even on Jupiter's most intense aurora, or even over Jupiter's most intense aurora, upward electron intensities. So these are intensities, these are electrons that move away from the planet and do not create emissions, often are much, carry with them much more energy flux than the precipitating counterpart. And so if you focus on the right panel here, its intensity is a function of time. And this is just to show that the energy spectra of the upgoing electrons are orders of magnitude more intense than the precipitating counterparts. That might be a function of the altitude crossing and where the acceleration region is located. But nonetheless, what's really interesting is that the intensity content of those upward electrons far outweigh kind of the intensities of the electrons found in Jupiter's very intense radiation belt. And so that's kind of the community right now is asking the question, can upward electrons associated with auroral processes be a seed population for the very energetic radiation belts at Jupiter? This here shows that even though that there's maybe 3 to 4 orders of magnitude more intensity in those auroral electron beams, even if you only maintain a few percent of that and that are inward transported, you can still generate the intensities in the radiation belts. All right, and then finally, we'll close off the main auroral region with the idea that Jupiter exhibits very Earth-like kind of manifestations in the auroral region, which is very interesting because the energy and mass flow in the system is very different. At the top just happens to show a montage of auroral emissions in the north polar region associated with what is called the substorms, and this dipolarization and injection of plasma in the inner magnetosphere. And so you can see that there's these spots, there's a brightening, and then there's these bead-like features that form. And then during other phases, you can kind of see what's called the expansion phase, very bright signatures as well that move more equatorward. So then for Earth, you can also see very similar structures as well. So these bead features and also this expansion phase. And so it's kind of a big open question of how you can produce similar auroral emissions based on very different dynamics. Lauren, I should probably leave some time, right? So I think what I'm going to do is skip to the end, and then whoever is around later, I'd be happy to talk some more. So I'll leave the summary up. I'll stop there, and then I welcome questions.
Great, thanks so much. Yeah, I wanted to just leave a few minutes for folks who may have questions or comments that can't stay past 1:40. Yep. So we'll open the floor, and if you have a question, feel free to raise your hand or put it in the chat. And I'd love to start if any grad students have questions or comments they'd like to ask. And if not, we can move to non-grad students. So go ahead, Dan.
Yeah, sorry I had to tune in late, but long ago there were models of a unipolar generator for Io moving through the magnetic field of Jupiter. And I guess I the of that kind of a source of generation for energetic electrons associated with that unipolar kind of behavior.
Dan, I think it's Dan Baker, right? So
That's correct.
Lauren, I heard some weird feedback on my end. Did you too? I'm sorry, Dan, your question kind of came in and out, but yeah,
yeah, so can you hear me okay now?
I can, yes.
Okay, yeah, so long ago there were models of as Io moved through Jupiter's magnetic field, that it was acted as a unipolar generator, and it ought to generate hundreds of keV electrons by that unipolar kind of generation mechanism. Do you see evidence of that kind of a behavior in any of the data you're getting from Juno?
Yeah, there's definitely energetic electrons that are associated with the Io's, main Alphane wing and the tail, which is likely set up from that Alphanic interaction locally near Io. We see the low energy electrons that go up to, tens of keV, 50 keV that precipitate. But the energetic electrons, the measurements aren't as instructive as we maybe as we want them to be. Instead, what really is interesting at the very high energies from the energetic particle standpoint is the association of accelerated protons that are moving away from Jupiter as a consequence of that interaction. Right now, we think it's because of the ion cyclotron waves, but Joachim Sauer and his group are also investigating the non-resonant Alphane interactions, and how those kind of cascade into the scales associated with the ions. I'm somewhat ignorant on those ideas, but hopefully that helps answer your question. So we definitely see imprints of energetic electron acceleration up to tens of keV from the Io interaction.
Okay, well, I'll give the papers a closer look and see whether there's any of the unipolar behavior there, okay?
Okay, thanks.
Thanks.
Great, thanks. And it looks like, John, you had your hand up next.
Hi, John Sebastian. Thanks, George. So I wanted to ask about this upward going electron current. And I was sort of wondering can you disentangle potential radio signatures associated with the upward current versus the downward current? Those different, is that possible?
Yeah, disentangle the different what? Again,
radio signatures.
Right.
Cyclotron maser emission.
I wish I was more of a waves expert. So cyclotron maser has been identified by the waves team, and they have mapped out the source regions. Now I do have some papers that I can send to Lauren to pass along, but I'm a little ignorant, so I can't really speak with confidence about that, unfortunately. So I can speak about the particle signatures associated with those different current regions, but not the plasma waves.
Right. Okay. Thanks.
No problem.
Okay, so it is 1:40. I see there's a few comments or questions in the chat, but I wanted to just pause here for folks who do have to go. And thank you all for attending, and thanks, George, for the colloquium.
Yes, you're welcome. And apologies for going over. I tend to do this, so I should know better.
Yeah, so thanks again. We'll stop the recording here, but then if folks want to stay on and have other questions or